Okay, let's look at the last couple topics in today's lecture regarding matrix inverses. So I want to list a couple of properties of um, inverses. You'll find these listed in your book. I'm going to use kind of shorten them up a little bit. It is assumed that the inverses exist in each case. Um, the inverse of the identity matrix is the identity matrix. Um, the inverse of an inverse is equal to the original matrix. Um, the inverse of a product of two matrices, and they're both, the inverses are assumed to exist. A and B would both be square and of the same size. Okay, that's equal to the product of the inverses in reverse order. Remember, we had a similar result for the transpose. The transpose of a product was equal to the product of the transposes in reverse order. And more generally, if you have A1 times A2 times dot 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 AK and want the product, or I'm sorry, the inverse of that series of products, that's equal to the product of the inverses in reverse order. Um, the inverse of a matrix to the kth power, so this would represent, the square cube of a matrix, is equal to that same kth power of the inverse. The inverse of a scalar times a matrix, so A is just a number here, is equal to 1 over A times the inverse of A. And then finally, the last one I'll list here is the inverse of a transpose is equal to the transpose of an inverse. And I'll work through an example problem in just a second, illustrating how you can use these properties to solve matrix algebra problems. I want to also list some equivalencies. So the following are equivalent statements. For an n by n matrix A. In the text, this is called the inverse theorem. So the inverse existing, that's equivalent to saying that the solution to the homogeneous system is x equal to 0. The only solution is the trivial solution if A exists, if A inverse exists. Equivalently, the reduced row echelon form of A is equal to the identity matrix, that A can be reduced to the identity matrix by a series of elementary operations. That's equivalent to saying that the inverse exists. Similar to 2 is that the solution to a linear system of equations that has a solution. And indeed, we've seen what that solution is. It would actually be A inverse times B. If a matrix B exists such that AB is equal to I, then B is the inverse of A. And finally, the fact that the inverse exists is saying that the rank of A is equal to n. We're saying that the matrix is of full rank. Again, A is an n by n matrix. I'll just point out a couple things I guess I've probably been remiss in Octave, you can compute the rank of a matrix just with the function rank. Again, you can get that information from the reduced row echelon form. It's equal to the number of leading ones in the reduced row echelon form. And then probably more importantly for this section, we can compute the inverse of a matrix using this notation, inverse of A. So, the product of A inverse B would be, you could write that as inverse A times B in Octave or MATLAB. Okay. I want to just show a simple example. I've modified it a little bit from one in the textbook. This is exercise 2.4.5D, okay, where we're asked to find A, when we're given this matrix equation, I minus 2A transpose inverse is equal to B. In the problem in the text, B is actually a specific 2x2 matrix, but I just want to work through it in general. I'm going to assume that B inverse exists here, and so the first step in is solving for A is undo the operations. So I'm going to take the inverse of both sides. Of course, the inverse of an inverse is the original matrix. So we get this result. Okay, and then now I'm going to isolate again this 2A term. I'll subtract B inverse from both sides and actually move the 2A transpose term to the other side. Again, working my way toward A. I'm going to divide both sides by 2. I minus B inverse. And finally, relying on the fact that the transpose of a transpose is equal to the original matrix. The transpose of a scalar times a matrix is just the scalar times the transpose. So this is illustrating how we can use the properties not only of inverses but also transposes to solve a matrix algebra problem for A. Okay. One final thing that I'll mention is with regard to transformations. It was another way to view a matrix vector operation as a transformation on the vector. Here, and since we're talking about inverses, we're going to be dealing with transformations from an n-dimensional space to an n-dimensional space. So, for example, let the transformation T be represented by a matrix transformation from Rn onto Rn. For example, that corresponding transformation here we're saying can be represented as a matrix operation. And let another transformation, call it T prime, equal TB, is also a mapping also maps a vector into from Rn into Rn, and of course, so we'll say y is another vector, and we can represent that as by. Then, if it's true that this T prime transformation on the Tx transformed vector is equal to x, or equivalently, representing this by matrices, Bax is equal to x, then B is equal to A inverse. Okay. which provides a geometric way to actually find an inverse matrix. And so probably best illustrate that with an example. We'll use exercise 2.2.22 here. The particular example was called called X expansion. So we're given the vector in 2 dimensions x, y. The transform vector was ax times y. Okay, that can be represented as a matrix transformation ax, where A is actually equal to A0, 0, 1 times xy. We'll see that that gives, this row times this column gives ax, and this row times that column gives y. So this is the matrix of the transformation, A0, 0, 1. Actually, this wasn't the problem. The problem was to find the inverse transformation, T prime, that would take AX and transform that back to XY. Again, perhaps a pretty trivial example. In other words, find the matrix B so that B times AXY gives us XY. Okay. We can see, kind of by inspection, here, that really if the original was X expansion, we need to do X compression. And if we make this element 1 over A and 0, 1 over A times AX is going to give us X, plus 0 times Y, that gives us X. And then in this bottom row, we would need a 0 here and a 1. 0 times AX plus Y would give us Y. We'll see that the corresponding matrix of the inverse transformation is 1 over A, 0, 0, 1. Okay. Well, the implication of the theory above is that B is equal to A inverse. And indeed, you can verify that by either left or right multiplying B by A. And you'll see that, and this is true. So it provides, kind of a geometric method for coming up with a matrix inverse. Of course, in this particular problem, we could have used our original technique for finding the inverse of a 2 by 2 matrix that was given. We've also looked at a more general technique for reducing the augmented AI matrix to I and then A inverse. We could use that method as well. Any of those would actually give us the same result for this matrix inverse. Okay, I think that's going to wrap things up for today. So 3 kind of short videos covering this section on matrix inverses.